Let's do some friction problems. Properties of friction. It says that right above number 1, so I thought I'd say those words in an excited manner. They're like bold. So the floor of a railroad flat car is loaded with loose crates. Sounds like a bad plan from the start. Having a coefficient of static friction of 0.25. If the train is initially moving at a speed of 48 kilometers per hour, probably going to have to convert that. In how short a distance can the train be stopped at a constant acceleration without causing the crates to slide over the floor? All right, well, let's see. If you imagine the train is going this way, because things tend to move to the right, then the force diagram, if it was moving at a constant velocity, would be some gravitational force of, let's say, this is the force acting on some crate that's sitting in the car, let's say. So let's say it has a mass of m, and the normal force would be mg also, because there's no movement up, down. Now, what if it was moving this way but slowing down? If this is going to slow down to a stop, there would have to be some unbalanced force this way on the crates. And what's going to provide that force? Well, there's nobody there to push on it or anything, and they're not up at the front of the car, so it can't be like a normal force from the front wall of the boxcar. So if the boxcar or the crate is just sitting there on the flat car, it must be this friction force here. And if it's not going to slip, then it must be static friction. Right? So, what is the maximum static friction force? Well, that's the coefficient of static friction times the normal force. So what is that? It's 0.25 times the normal force, which is mg. And we want to know about bringing this thing to a stop. Well, first of all, 48 kilometers per hour, that is 48,000 meters in 3,600 seconds. It's about 13 meters per second. All right, so if you want to bring this to rest, well, I guess what we could do here, we could say, also we have one more step to do here. Sum of all forces is equal to mass times acceleration. So if the only force is that friction force that way, there's only a loser. So winners, there aren't any, minus losers is equal to, or I guess I'm putting that negative sign in there because I want to make sure that this, one way or another, the acceleration is the opposite direction of this velocity. So it needs to come out to be negative. Friction is 0.25 mg. The m's cancel, so my acceleration here is negative 0.25 g. And what are we looking for? What's the stopping distance? How short a distance? So we're looking for that. And then back to kinetics again. That looks like Vf squared equals Vi squared plus 2a delta x. So Vf, that's 0. Initial velocity is 13. The acceleration is negative g over 4, 0.25 g. That's a quarter of it, however you want to write that. And times delta x. So math. That does not look right, the thing that I have there. Hold on a wee second. No, I think I missed, what did I do? Oh, I think I see what I did. Need to do 169, and then I'm going to be dividing by g over 2, which is 4.9. There we go. And delta x is about 34.5 meters. The book, they have 36 meters. They treated their sig figs a little different than I did. So that's the reason for that discrepancy. All right, great. Number 3. Bedroom bureau with a mass of 45 kilograms, including drawers and clothing, rests on the floor. The coefficient of static friction is 0.45. What is the magnitude of the minimum horizontal force that a person must apply to start the bureau moving? The mass of this thing was 45 kilograms, fully loaded. So the maximum static friction force is the coefficient times the normal force, and that coefficient is 0.45, and the normal force would be equal to mg, so that's that. So that's the maximum friction force. So that's, if you want to overcome, if you want to break this thing free, you're going to have to match that and just barely exceed that, and that will break it free, because this is the maximum static frictional force. So that is 0.45 times 45 times 9.8, about 198 newtons. Our book made that 200. I'm going to go with the 198. And part B. If the drawers and clothing with 17 kilograms mass are removed before the bureau is pushed, what is the new minimum magnitude? So we're going to take out 17 kilograms. So that's going to be 0.45 times, what's that minus 17? Is that 28? 0.45 times 28 times 9.8. So now about 123. So there you go. You want to move your dresser around? Maybe you should take the stuff out of the drawers. And that's it. All right, number 5. A 2.5 kilogram block is initially at rest on a horizontal surface. A horizontal force of magnitude 6 newtons is applied, and a vertical force, which they're calling P, some kind of pull upward, I guess, is then applied to the block. Coefficients of friction are 0.4 and 0.25. And we want to determine the magnitude of the frictional force acting on the block. If the magnitude of P is 8, 10, and 12. All right, and I think I forgot to write down that the mass is 2.5 kilograms. I'm going to make a little force diagram here. So this is 2.5 G. The normal, now this P is upward here, and the bigger the P is, the smaller the normal force is going to be, right? Because those are both in the same direction. They're both helping out to balance that 2.5. So that Fg, our force of gravity, is going to equal the normal force plus the pushing force. Right? And then, or the pulling force, pulling upward. And then this force is 6 newtons. So for part A, the pulling force, oh, let's just get a number on this 2.5 G, sorry, 2.5 times 9.8, that is 24.5 newtons. So in this one, the normal force, since this upward pull is 8 newtons, and this is 24.5, this would have to be 16.5, because those must be matching, balancing this. Okay, so the first thing we have to do is see, is there enough static friction to keep the block from moving? So what's the maximum amount of static friction available? Is the coefficient of static friction times the normal force. And in this case, that is 0.4 times the normal force, which is 16.5. 0.4 times 16.5 is 6.6 newtons. Is that enough to keep it from moving? Yes, because it's bigger than this. So how much friction will there be? This is enough. Yay. So the force of static friction is equal to 6 newtons, not 6.6. Why not? This is just what the maximum is. How much is there actually going to be? Well, there's going to be as much as is necessary to keep it balanced. There can't be more friction than there is this pulling force. Then this person would pull, friction would win, and it would start accelerating backwards. That is just not ever going to happen, not in this universe or any other one. As far as not anyone I've been to anyway. What about B if the upward P force is 10 newtons? What about that? Well, if that upward pull is 10 newtons, then the normal force to match this would only have to be 14.5. And that means my maximum static friction force would be 0.4 times 14.5. 5.8. Is that enough to balance this? No, not enough. And that means that it's not going to be a static friction situation. It's going to be kinetic. So now I have to figure out, okay, not going to be static. It's going to be kinetic. So that's 0.25, the smaller coefficient, times 14.5. Which is about 3.6 newtons. And for part C, is it 12 newtons now? So now the normal force is only 12.5. And I definitely know now, I'm just going to jump to the kinetic because I know there's no way there can be enough static friction. We already didn't have enough when it was only pulling up with a force of 10 newtons. So the kinetic friction will be 0.25 times the normal force. What did I do? So that's 3.25. Or 3.3, I bet they have in the back of the book. Oh, they have 3.1. How'd they get 3.1? Well, whatever. So there you have it. Number 5. All right, number 7. A person pushes horizontally with a force of 220 newtons on a 55 kilogram crate to move it across a level 4. Floor. 55 kgs. Person's pushing with a force of 220. Coefficient of kinetic friction is 0.35. What's the magnitude of the frictional force and the crate's acceleration? Let's make a little free body diagram here. Force diagram means the same thing. This would be 55G. That's the gravitational force. And the normal force is going to match that because there's nothing else going on. No ramp, no other force pulling upward or something like that. And this is totally horizontal, so it's not going to affect that. Speaking of that, 220 newtons of pulling or pushing, whatever you want that P to stand for. And then I got some friction. How much friction do we have? Well, I guess that's part A. The kinetic friction force is going to be mu times the normal force. So 0.35 times 55G. Got 189 newtons for that. And then for part B, they want to know what's the acceleration. Well, sum of all forces is equal to mass times acceleration. My friend Isaac told me that. And sum of all forces, I've got the pulling force winning minus friction losing, and plugging in some numbers. I got 220 minus 189 is equal to 55 times A, so that's 31 over 55. Looks like the acceleration is going to be about 0.56 meters per second squared. All right. Last one from this little group of problems. All right, now I got a block. Instead of being like pulled by a rope up at an angle like that, this one's being pushed like down into the floor like that. And the magnitude of this force is 15 newtons, and the angle, sorry, it does not look like it in my picture, is 40 degrees. The books looks a little shallow too for 45 degrees. Not going to lie. Coefficient of kinetic friction. Okay, so I think we're going to need to make a force diagram here in a second. Kinetic friction is 0.25. We want to find the frictional force and the acceleration. Okay, so here's the diagram. This block is on a flat surface, not a ramp. So my axes go like this. If it was a ramp, then they would be tilted to line up with the ramp. So I've got the force of gravity, because it doesn't care what we're doing. Do I know the mass of this thing? I do, 3.5 kilograms. Right, and then the normal force would be 3.5 G also. No, it wouldn't, because this is pushing down. And if that's pushing down, then if we map out the components of that, you can see that this right here, this would be 15 cosine 40. And this would be 15 sine 40. So the normal force here is going to have to balance both of these. Again, if you want to add some, kind of map this onto things that make sense, add some intuition into this. If you think about this box resting on like a bathroom scale, if you push down at an angle on it, then that is going to increase the reading on the scale. And the reading on the scale, that's what the normal force is. That's how hard the floor or scale has to push up on it. So let's see. I got how much normal force? I got 34.3 plus 9.6. And that's going to make the situation a little stickier. No pun intended. Because the force of kinetic friction is equal to mu times the normal force. And that coefficient is going to be multiplying by a larger normal force. Larger than if there was nothing pushing down, right? If it was just sitting there, or if this force was horizontal, then the normal force would only be 34.3. So 0.25 times that is about 11. And that means, I think that is the answer for A. Make sure that I'm answering the right question. That is the right answer to the right question. And for part B, they want to know the acceleration. So sum of all forces is equal to mass times acceleration. What's going on here? Well, I've got the 11.5. Everything balances out in the up-down direction. No motion in that direction. 11.5 minus the friction force is equal to mass times acceleration. So about 0.14. And that is all there is to it, the friction force. So I think a good idea to just understand at this point, all we have done from Chapter 5 until now is added in this new trick, new mathematical model. How do you quantify the friction force?